On this page of our notes, we're going to be going through specifics related to good experiments. Now, I know that you have learned this information in the past. So for those of you that didn't do well with this in the past, then hopefully this is going to clear up some misconceptions. For those of you that already have done well, like on that inquiry pre-quiz that you took, there are some specifics that you need to know that I require you to do for this class. Now, in the past, you maybe have had to list the steps of the scientific method, but that's not something you're going to be asked to do. You just, in general, need to know what is some of the good criteria of good research or good experiments. First of all, a good experiment is always going to have an independent variable that is being tested. I like to remind students to think of I for independent, I for, so let's write I for what I change. If I'm setting up an experiment, I'm going to set up several parts to this experiment. And between each of these parts, I'm going to change one thing between them. That one thing that I'm changing is representative of that independent variable. Now, all other variables are going to be remaining constant. We'll talk more about constants here in a second. One thing I want to point out, when you're setting up these different parts of the experiment, these different parts are called your experimental groups. When you're creating these variations between these experimental groups, these variations have to be realistic. We'll talk about that more here in a second. The dependent variable, I want you to think of D for dependent variable, D for data that I'm collecting. So if you think about it, as you're doing this experiment, you're going to be monitoring something. You're going to be collecting data. You're going to be writing numbers down in a table. Whatever those numbers represent are going to be the dependent variable. So if you're writing down the number 2, the number 7, the number 3, and let's say that you're testing pH, those are the different pHs, and that data that you're writing down, 2, and so on, that's representing the dependent variable. You're testing pH. So change in pH would be the dependent variable. Now for the constants, these variables that need to be held constant, constant means the same. So the different variables that have to be the same for each part of your experiment are what we consider constants. If you altered these constants and they weren't the same, then it would be unfair for different experimental groups. Whenever you're asked to find errors in your experiment or errors in the design of your experiment, one thing I tell students to do is go and look at your constants. What are some things that you indicated needed to be constant, but it was impossible for you to hold them constant? Or there was going to be some slight variation in these variables and it wasn't something that you'd be able to control. Those would be good things to talk about when you're talking about errors in your experiment design. Students often get constant and control group mixed up because they both start with C. The control group is going to be one of your setups. It's going to be one of your experimental groups, and that setup is the one that's under the most normal or average conditions, or it's the group that you don't do anything additional to. The reason why you have to do a control group, and sometimes you need to be able to explain this, is that you need data that is like your basic data. It's a reference in which you can compare these other experimental groups to see if what you did in that experimental group is actually having an effect. Whenever you're going to identify the control group in this class, I'm going to usually make you circle one of your experimental groups so you understand the control group is one of your experimental groups that is under the most normal or average conditions. Now let's go through an example test and identify these key parts of an experiment. So here is the problem. It says students decided to test if temperature affects the number of times a cricket chirps per minute. So let's identify the independent variable. Remember, it's what I make different. And since I'm going to test temperature, I'm going to put these crickets in different environments that have different temperatures. So my independent variable, what I'm making different for each of these crickets, is the temperature. Now, if you just write temperature, I'm going to mark through it. I'm going to use at least 3 words or 2 words. Let's put the temperature of the environment. Sometimes when you just put one word down for your IV, for your DVs, for constants, it's not enough information. You need to be more specific. Now, if I'm actually setting up this experiment and I'm identifying these different temperatures, I have to make sure that the temperatures I choose to test are going to be realistic. And I talked about that a little bit earlier. I want to make sure that these are realistic. So what temperatures do we want to set for these different experimental groups? Let's review a little bit about Celsius, since most of the time when we're dealing with temperature, we're going to be dealing with Celsius in science class. Remember we said that 0 in degrees Celsius is the freezing point of water. So would it be reasonable to set up a cricket and put them in 0 degrees Celsius? Well, you're going to kill your cricket. You're going to freeze it. There's no way to count the number of times they're chirping if they're dead. So we would not set up a cricket at 0 degrees Celsius. So no, that's not a realistic treatment for this type of experiment. We know that 100 degrees Celsius is the boiling point of water. And again, you cannot count number of chirps if you have a dead cricket. So 100 degrees Celsius is not a realistic treatment for this experiment. If you remember, room temperature is about 23 degrees Celsius. So let's set up a cricket in an environment. We could put them in an incubator and set the incubator to establish the temperature at 23 degrees Celsius. If you remember body temperature is getting close to about 100 degrees Fahrenheit. Crickets would be able to survive that. And in Celsius, that's about 37 degrees. If we want to go a little bit warmer than body temperature, a little bit warmer than 100 degrees, we could go up to about 42. So we're getting pretty warm there. We probably wouldn't want to go much above 42. As for getting colder than room temperature, we don't want to go down quite to 0. But we could probably choose to test something around 10 degrees Celsius. So we've established some realistic treatments for this test. If you're asked to indicate what treatments or experimental groups you're going to test, what we mean is you would just indicate what you decided to test for these different temperatures. So we'd write 10, 23, 37, and 42. Now let's talk about some constants so that we have a good experiment here. We would want all of our crickets to be the same age. So let's write age of the cricket. So age of cricket is fine, but we want at least 2 to 3 words here when we're describing things or variables that need to be held constant. Something else that would need to be constant would probably be the size. And if I say size, you might think size of the cricket, but I was going to say size of these incubators. That's why you have to give more than one word, because if I write size, you might think I'm talking about the size of the cricket. But that would also be something that we would want to keep constant, the size of the cricket. Something that would be critical would be the activity around the cricket. Because as you all know, if you have a cricket in your garage and you open the door, that activity usually causes that cricket to be quiet. So it would be hard for us to then effectively count the number of chirps and if really it's temperature that is affecting that. Remember I mentioned up here that whenever you're trying to figure out experimental errors, that it's handy to use your constants because there's some things that's just going to be impossible for you to keep constant. So let's go down here and analyze the experiment and see what are going to be some possible sources of errors. One would be, I would say this one right here. So again, this should be a constant. It might be hard for you to keep the activity around the cricket or around each cricket exactly the same. So let's indicate that. But we're not just going to put activity around the cricket. We can start with that, but that doesn't really explain why this is an error. Let's put the activity around each cricket would be hard to keep constant. If you just write the constant over again, activity around the cricket, then I'm going to mark through it and I'm going to have you add more because that doesn't really explain why that's an error because I know the activity around the cricket should be the same. So again, you have to put would be hard to keep constant to indicate why that is an error. Something else that would be hard to keep constant would be the age of the crickets unless you actually raise the crickets from the time that they hatched out. You probably are going to go to a pet store and buy crickets. So it'd be hard for you to keep specifically the age of each cricket the same. Now, before we go on to the next page, I skipped the dependent variable, so let me come back and talk about that real quick. As this experiment is taking place, I'm going to be somewhere by the Cricut with a clipboard, and I'm going to have my table. I'm going to be recording the data. Remember, dependent variable, I want you to think of data. D for data, D for dependent variable. The numbers that I'm going to be writing down are going to represent our dependent variable, and I'm going to be writing down things like 7 chirps, 10 chirps, and so on. So the number of chirps, or the chirp rate, would be our dependent variable for this experiment. That is the data that we're collecting. Now, usually when we start an experiment, we have a question that we want to test. But the reason why I haven't talked about writing testable questions is because you have to know the independent and the dependent variable before you can write a testable question. An easy, good format to use when you have to do this on the EOC exam, which you are probably going to have to write a question on the EOC exam on part 2. A good format to use is how will the IV affect the DV? And you're not just going to write IV and DV in there. You're actually going to figure out the IV and DV and plug it in. So for this example, we're going to state our question is, how will temperature of the environment, I'm just going to put temperature now to save time, how will temperature, so there was my independent variable right here, affect chirping rate or number of chirps in crickets? This is the data that I'm going to collect. There's my dependent variable. We haven't written a hypothesis statement yet for this experiment because, again, you have to know the independent variable and the dependent variable in order to write a correct hypothesis statement, because you need to be able to put these two things in this hypothesis statement. You have probably learned that to write a good hypothesis statement, you need to use the words if and then. And we're going to go ahead and keep teaching you to put if and then in your hypothesis statement, but eventually that might change as you get a little bit older. You don't necessarily have to put if and then in there, but you do have to indicate the IV and address how it's being changed, and you have to mention the DV and predict about it. So let's look at a couple formats that you can use. So first of all, format 1, it says if you test and you kind of describe what you're doing, then predict about the dependent variable. If you do that, you're going to have a good hypothesis statement. I'm going to write an example of a good hypothesis statement using format 1. So it starts off, if you, and we're just going to describe our experiment. So let's write, if you put crickets in different temperatures. Now, I like to be specific and indicate those temperatures. I think we chose 10 degrees Celsius. We had a 23 degrees Celsius. I believe we had a 37 degrees Celsius. And then I think we had 42. Okay, so I just described what we did. And then I'm to the then part, comma, then. Now we have to predict about the dependent variable. We have to predict about chirping rate, or the number of chirps. So if you put crickets in different temperatures, then let's say I think that at 42 degrees Celsius, they're going to have the highest chirping rate. Then I'm going to put that. That's my prediction. And then I'm going to say, then at 42 degrees Celsius, the cricket will have the highest chirping rate. I'm just going to put rate. Basically, you're going to predict whatever you think is going to happen. Looking at format 2, students really love format 2. It doesn't work for everything, but when it does work, it's pretty easy to do. It says if the independent variable, so you plug in the independent variable, is, and talk about how you're going to change it. Are you going to increase it, or is the independent variable going to decrease? Then the dependent variable, we're going to plug that in, will increase, decrease, stay the same. So I'm just going to say a hypothesis that goes with format 2 for this test. If the temperature of the environment is increased, then the chirping rate will decrease, or whatever I think is going to happen. The biggest mistake I see students write is indicated right here. They're going to say, if you test different temperatures, and they're not very specific about temperature. Are you increasing temperature? Are you decreasing temperature? So you need to be specific of how temperature is changing, or you can even list the different temperatures. And then students will also say, then you will see which temperature causes more chirps. That's not a prediction of what you think is going to happen. You need to be specific about, is chirping rate going to go increase? Is chirping rate going to increase? Is it going to decrease? Or is it going to stay the same? Just not, you're going to see what's going to happen.